4-8, day 1. Got 4 examples to work through, and we have kind of done applications in bits and pieces. We did a lot in section 3, and since then we haven't done a ton. And so in section 8 we really get back to it, and it's all applications all the time. Really, I've got a couple new things for you to see. Those are going to wait until day 2. Okay, so what I'm hoping you see out of this lesson is some problems that are fairly similar to section 3, and then a couple others that are kind of the same ideas that we did, maybe a tad more complicated than the ones that we saw, earlier in the chapter. Not so much in this first one, though. This, I'm thinking, is just a great place to start, where, section 3 was all about solving right triangles, and that's all that's going on here. Like right off the bat on this problem, I would hope that you'd see the easiest part to solve would be that angle B is 55.8 degrees, coming from 90 divided by 34.2. So then I'd turn my attention over here. I'm going to go ahead and use this angle. And, trig equations don't tend to be super tricky to solve. They can be a little bit tricky to set up. But here what I'm after is I see tangent of 34.2 is the opposite side. And I'm really interested in that adjacent side because I know it. And that leaves me with only one variable. And therefore side length A would be 19.4 times the tangent of 34.2 degrees. You can already see here that having a calculator that's set to degree mode is a good idea. Happens a lot with applications. I mean, we're working within the context of right triangles, so if you wanted to relate this to the unit circle, everything today is going on inside quadrant 1, okay? Which basically means if we don't see a 30, a 45, and a 60 degree angle, we're not going to use the unit circle, and we're going to have to use decimal approximations, like right here. That side is approximately 13.2. And then at this point, to get the hypotenuse, you could set up another trig function if you wanted to. And if you prefer going about it that way, that's fine. There's nothing wrong with doing that. I'm writing out the way that I feel like what most of you would do, which would be to use the Pythagorean theorem, another perfectly valid way to solve for C. There's C squared. I'm going to keep rounding to the nearest tenth. This whole problem I've just kind of been using the nearest tenth. And there you have it. Just to kind of double check our work, C should be the longest side. It is 13.2, 19.4, and then there's C at 23.5. Now that actually wasn't an application problem, if you noticed. But it did take us back to right triangle trigonometry. The next 3 are true application questions that have some kind of word problem and description to them. Okay. Here's the deal with this context. We've got this fire truck, and we are after 2 pieces of information that kind of seem safety related. We're given that for this ladder up against the building, as far as making like a safe rescue of somebody out of a window, the angle with the ground shouldn't be any steeper than 72 degrees. If it's more than that, then the ladder's kind of too vertical. Okay, we're after 2 things here. We're going to call this B, which is to achieve that angle of 72 degrees, how far away does the truck need to be parked from the building? And now it marks it over on this other side, but I'm going to bring it over here. Here's A, which is how high up the building the ladder could reach. Okay, now notice this is another big piece of information. We know the ladder is 110 feet. I'm going to go with the maximum height first, so I'm going to focus on A. And both of these, we got two separate problems that we have to do. That's part of the complexity of this one, is you got to make sure you're clear about that. I'm going to get A first, and I'm going to look at it from the 72-degree angle. And as I'm kind of setting up my trig function, I know that the hypotenuse is 110, and I'm getting the feeling like that's going to be significant, that it's going to be a side that on both calculations will be used. And so when I'm thinking through SOHCAHTOA, that makes me think tangent is probably not going to be a factor, and it's going to be sine or cosine, the ones that I'm going to want to use. I'm going to keep labeling here. A is opposite. B is adjacent. So it looks like if I want to get A, I'm going to take that the sine of 72 degrees is A. That's what I'm looking for. Over 110. That obviously would need to go into a calculator, and that would tell us how far up the building we can go. Up to close to 105 feet is about how far this ladder could reach. Now, as you look at the diagram, you might notice that there's a little gap right here that's sort of unaccounted for. So, I mean, it doesn't tell us how tall the truck is, or what that, how far above the ground does the ladder start. So we can't really factor that in. We know that this number right here of 104.6, that is really 104.6 feet above the truck, not above the ground. But without knowing, this point right here, the base of the ladder, how high that is above the ground, it's about all we can do. Now, how far away the truck should be parked, pretty simple adjustment here once I had all the sides labeled. That side is adjacent, so notice the whole setup basically looks identical. The only thing in the whole process that's changed, it's cosine function now. And that comes out to be 34 feet. So within all these safety regulations that we have, that's how high the ladder can get, 104.6 feet. And to achieve this, it's fairly important that that truck is parked. It shouldn't be parked any closer than right around 34 feet from the base of the building. This is another one that kind of has two parts to it. Different from the other one because it's not just like two separate calculations. What we're after on this problem is this. We've got the smokestack on the height of the building, and what we're after is relatively simple. We want to know how tall it is. Okay? But the information that we have to do this isn't exactly ideal. Okay, we just kind of have to make do with what we got. 200 feet from the base of the building, we have an angle of elevation to the top of the smokestack, which is 53 degrees. And then we have one to the base of the smokestack, or the top of the building, which is 35. Okay? I'm going to kind of take two approaches here. I'm going to go off this first angle of elevation. And in blue, you have what I'm going to call the big triangle. Goes all the way to the top of the smokestack. And then in red, if you go off the angle of elevation to the top of the building, that one's going to be called the little triangle. What I'm going to do first is focus on this big triangle, and I'm going to say tangent is the ratio I want. Tangent of 53 degrees is something over 200. Okay? This something is the opposite side of the big triangle that is really comprised of two distinct lengths. Up at the top you have the smokestack, and then at the bottom you have the building. Okay, now just because the diagram kind of looks like they're split evenly, don't make the jump that they're 50-50 and the two are the same thing. Okay? That might be the case, but from what we have at this point, we can't tell. So now we'll just go 200 times tan of 53 is the sum of those two parts, S and A. Comes out to be, and this is once again calculator, 265.4 feet. Okay? That is not our answer, but it's really helpful. We now know ground to top of the smokestack is 265.4 feet. Okay? Let's turn our attention now to what we're calling the little triangle, the one in red. And I could set up one that's really, really similar, except I'm going to use the angle of elevation that's 35 degrees and then just say A over 200, right? Because that angle of elevation goes to the bottom of the smokestack, so I'm not including that height. And then we have 200 tan of 35 equals A there is the height of your building. It's 140 feet. That is also not our answer, because if we relate this back to the whole discussion we're having with variables, I probably should have pointed this out earlier. What we are after is S. Okay? We have S plus A, and we have A, which, you know, we are awfully close to what we're after here. So we could now say, if I go back and kind of basically take this and plug that in, we would know that 265.4 equals S, that's what we're after, plus 140. Subtracting 140 from both sides, there we have it. The smokestack is about 125.4 feet. Okay. Again, a little bit more complex problem with right triangles. Notice the multiple parts to it. Okay. The last two here have kind of had two different things going on that, you know, we would expect that you could manage. Each individual part, though, really is just its own SOHCAHTOA problem. Okay, and that's something really important that I want you to see. All right. The angle of depression this problem is looking at is right here. I'm going to call that theta. There it is. So this is kind of the transition between the two ends. I think from what it describes that like the deep end levels off and the, you know, there's a shallow end down here, and this is that transition between the two, which if that's the case based on the 20 meters, this is a really, really large pool. But now what I kind of like about this problem, and you guys don't necessarily get a whole lot of it from problems from your textbook, there's some information here that is given that we don't need. All right? Because what we're after is theta. Now, what I'm hoping you think when you're finding an angle is that at some point we're going to need to use an inverse trig function. Okay? None of the problems we've seen today have done that yet because, you know, if you go off the smokestack problem and the fire truck problem, we were finding lengths, heights and lengths. We weren't finding angles. Okay? That's not the case here. You know, total, this deep end hits 4 meters, and the shallow end, it tells us, is 1.3, but neither one of those are really all that relevant. What is a really big deal for this angle is how much depth we're going to add. That's going to be 2.7 meters. Okay? The other part is how long is it going to take to add that depth. Okay? We're going to add 2.7 meters of depth over 20 meters. Okay? The longer that length is, the shallower this angle is going to be, meaning closer to 0. If this were a very short distance, the 20 meters, if it were shorter, then this angle would be steeper. All right? Also notice up in the description the width of the pool is 12 meters. Again, not relevant. You know, it could be in some other problem about the pool, but not this one. All right, so I'm looking at it from theta, and as I pointed out, here are the two really important sides, 2.7 and 20, okay, which makes me think tangent. Now here we're going to do the inverse, but in this setting, well, I suppose, yeah, we still, I mean, as always when you take the inverse, you know, we talked through that in section 7, how you have to be a little bit tricky as to which answer you give. These kind of application problems always put you in quadrant 1, so you never have to worry about that. You know, you would be good to go to your calculator and just say, tell me inverse tangent of 2.7 over 20. Making sure you're in degree mode, and it will say 7.69 degrees, and you'd say, awesome, sounds good, I'll take that as an answer. It would be if the tangent value were negative and it put us in quadrant 4, that would be a different story, but luckily in these application problems, you know, that doesn't happen. You don't need to worry about it.